Congrats today for my collaborators in this project, Ian Longo, one of my undergraduate students who's worked extensively in the Cataraqui Cemetery in Kingston, Ontario, especially over the last year on a funded project to do high-resolution differentially corrected GPS mapping of the cemetery. And I also give regrets for Alexander Gabov, who holds up the sort of the conservation end of the project. He's a private conservator at a company named CSMO, and he's worked extensively on stone conservation projects. So just a brief introduction to this particular cemetery. The Catarqui Cemetery is the largest in Kingston, Ontario, and Kingston, Ontario was Canada's first capital before it moved to Ottawa. It extends over 100 acres with over 40,000 individual interments. I think the actual number is 46, 47,000 at the moment. It's still an actively run cemetery. The layout is mixed. It was rather topical this morning that Mount Auburn was mentioned. In fact, this was one of the models for the Cataraqui Cemetery, along with Mount Hope in Rochester. Those areas have a garden-style layout, although there are areas with landscaped rows. And there's also an extensive military section to the cemetery. The cemetery was incorporated in 1850, but burials go back at least 50 years before that time. And this has led to some confusion in terms of who is buried where and aligning headstones with the burial records. So like many historic cemeteries, I'm sure this goes without saying, it can be a bit difficult to match archives with the headstones on the ground. So the problem I was confronted with is one familiar to you all. Cemeteries are important to local and national history. I personally, coming from this as an outsider in ancient history and classics, I typically deal with things 2,000 years or older. I was really surprised about the sort of local passion for genealogy in Ontario and elsewhere. The second problem, of course, is insufficient funds for maintenance and conservation. Even though the Cataraqui Cemetery since 2011 has been listed as a National Historic Site in Canada, and a small area in the cemetery is also a National Historic Site where Canada's first Prime Minister, Sir John A. MacDonald, was buried, there is still not a lot of resources for the maintenance of the headstones. Some reference has been made already in the conference to the topple test that's actively applied in the cemetery by ground staff. If it can't meet 100 pounds lateral force, then the headstone goes down, usually face down in the cemetery, and there's simply no money to bring it up unless the families are willing to pay for it. As I said, there's poor documentation of the older stones. One thing we've noticed in working with the genealogists is often the death records don't accurately reflect the dates. The headstones really are the gold standard there. And even more interesting for me, someone who works in ancient epigraphy, writing on stone in Greek, Latin, and Semitic languages, mainly in the Middle East, is that the legibility is very poor. The weathering and, in some cases, vandalism severely reduces legibility and the utility of the headstones to identify the grave sites. So I thought a certain synergy could be developed here where I could apply some of the technologies I've worked on for rapid and accurate survey, epigraphic survey in the Middle East, where I work in Jordan to document petroglyphs and inscriptions. And I thought that some of these technologies could be profitably applied to local cemeteries. There's also, it goes really both ways because it's a very useful way for me to introduce undergraduates to this technology without having to bring them overseas. And we have lots of different types of headstones to work on, and we can tweak the technologies without having the great expense of overseas work. So in essence, we needed an inexpensive technique for monitoring and documenting these heavily weathered headstones at various levels of detail. So in the case of the inscriptions, we want sub-centimeter levels of accuracy. And then at a larger scale, in terms of placing the headstones within the landscape, we wanted something that could be quickly deployed at the scale of tens of meters. There were really three proposed solutions we looked at. First was reflectance transformation imaging. It's something I've been involved with for about 6 years or so. It was developed at Hewlett-Packard Labs in 2001. The second is stereophotogrammetry, which has seen rapid growth in the last 6 or 7 years as high-resolution cameras and fast computers have become widely available. It's an old technique. It's more than a century old now, dating from the time when cameras were mounted on manual theodolites by Germans around the time of the First World War. And then the final solution for larger scale documentation is GPS geotagging of photos, which is a very cost-effective and is almost free way to generate high accuracy metadata. Experiments were conducted with these three techniques between 2010 and 2013. A lot of the data processing happened this year. With undergraduates and graduates from the Department of Classics at Queen's University, as well as graduates in the Master of Art Conservation program at Queen's University. I think one of only 5 such programs in North America, as well as some cemetery staff. It was really of paramount importance to me and my collaborators that we use these techniques with essentially untrained volunteers. We felt any technique that required highly specialized equipment and extensive expertise could not easily be deployable in local cemeteries. And we were pleasantly surprised by the results. So just a few remarks now on each of these technologies, why you would select them, and the underlying, dare I say, math involved in each of them. Reflectance transformation imaging requires multiple exposures from a fixed camera's position on a tripod with generally a strobe light moved at different locations around the headstone. These exposures, anywhere between 16 to 60 different exposures, are then combined in free software and open source software that produce a sort of pseudo 3D model where one can dynamically relight the headstone in software after the capture. At the heart of this technology, so-called highlight-based RTI, is a clever trick where a red or black sphere is placed in the frame of the photograph, red and black because they're easily available through pool and snooker gaming establishments. When the flash goes off, it puts a very small highlight into the ball. You can see it here. The software automatically detects the black or red sphere and places a red cross in the point of maximum light. And then this gives you a light vector for each position of the strobe around the headlight, or around the headstone, excuse me. The RTI equipment is fairly basic, a 35mm DSLR camera, and I should say that all of the three techniques we've used are built around digital SLR, sort of prosumer cameras. I know there are a lot of inexpensive and extremely high quality cameras available today, including cell phone cameras, but we think the DSLR is still the gold standard, not least because it's a highly modular technology where you can add on different piggybacking technologies. A wireless shutter release and flash trigger are also important because you don't want to have the camera move at all between the individual exposures. A tripod to hold the camera, 2 reflective black spheres, a high-powered flash unit. If we're working out of doors, we need essentially to overpower the sun, and a portable power unit, generally a lithium-ion portable power pack if plug-in power is not available. We like to use a monopod with the strobe light so we can lift it up rather high. A ladder is also helpful, and string because we want to ensure that the flash unit is an equal distance at each position from the headstone. This is an inexpensive technique, although I sometimes underestimate this. We already have studio facilities on campus, so most of this equipment was already available. Ab initio, you're probably looking at an expenditure of, say, $3,000 to $4,000 to get into this. Here's an example of RTI capture in the field with a group of students. You can see here the 2 black spheres. We have gray cards behind them to increase the contrast. The SLR camera here is mounted on a tripod. Here we see the monopod in action. with a high-powered strobe light there. The string there is placed to ensure that it's an equal distance from the stone each time. And the student is moving it around a notional hemisphere with respect to this vertical monument. From this, you can see one of the problems in implementing RTI in a cemetery environment. You can't get that true 180-degree hemisphere around vertical headstones very easily. The ground is in the way, and if you don't have a student who's about 6'4" like Kian here, it's a bit difficult to get those top shots. Sometimes we use ladders. Here you can see me up in a ladder with an umbrella. I'm trying to keep the sun out of those black spheres to prevent the sun from putting a highlight in that can confuse the software. What the software produces are surface normals, and it's worth here just looking at the underlying math of various 3D techniques for a moment. Here's a 3D surface, and at each vertex of this 3D surface we have an X, Y, Z point in Cartesian space. These points then can be linked up to form a continuous surface. This is what we call a mesh. At each point on the mesh, we have an arrow, or a vector to be more precise, that is perfectly at right angles with the surface, even a continuously curving surface. This is what we call the surface normal vector. The surface normal vector is very important if we want to dynamically relight a 3D surface in software, because it is the surface normal vector that bisects the incident and excident light. So if we want to shine a light within software on a 3D surface, we need to know what the surface vector is. RTI calculates only surface normals, not the other components like X, Y, Z coordinates, although at the end of the presentation I'll show you an example where we have been able to extract true 3D information from the RTI. The second technology is stereophotogrammetry. The easiest explanation of this goes back to stereopsis and human vision with two eyes, where we calculate distance by the parallax, or difference between a scene in the left and right eyes. The important thing to realize here is that stereophotogrammetry is different than 3D filming or 3D photography, or even our own stereovision. Our stereovision is limited by the base, or distance, between our two eyes. We're evolved from monkeys, and our stereovision is really only good to the out end of our arms, where we could grasp fruit and swing on branches. Beyond that, we use other techniques to determine distance. With digital cameras, this is not a problem. We can lengthen the base between cameras. We won't be using two separate cameras. We'll instead be using a single camera and taking shots at a distance from each other to calculate distance. The photogrammetry equipment is a little bit simpler. It's something we've been working with extensively over the last year. We use a Nikon D800E camera, just 36 megapixels, and a fixed 50mm Nikkor f1.4 lens. For this application, we do not really want to use zoom lenses. We don't want to change focal distance. And in fact, we don't want to change f-stop between the shots we're taking. That disrupts the photogrammetric parameters. If we wanted to get accurate scaling for the monuments, then we'd also put a scaling target, which could be anything as simple as a ruler or a stadia rod into the image. There are some fancier scaling targets that are easily printed off for this purpose. There are a couple different geometries we can use for capturing photogrammetry data. One is the convergent project. Think of cross eyes, where the two camera positions go in and focus on the individual headstone. This is very effective. We only need about 2 photographs. If we want to get full coverage of the headstone, sometimes we'll take 4, 5, or 6. This gives very high accuracy and doesn't require any special calibration procedure. It also gives us a good base to distance ratio. Base is the distance between the cameras, distance to the object. And this gives us the determination of accuracy in the crucial depth axis. We used to do a lot of strip projects where we take strips of overlapping photos, about 66% with 22% or 20% side lap of the headstone. We did this when we were working with 12 megapixel cameras. In order to calibrate the camera, we would have to take an additional set of photos where the camera was tipped up 90 degrees. I would take 2 photos like that and another 2 at 270. Given that we now have 36 megapixel cameras and they're widely available, we tend to use convergent projects. This gives you a sense of some of the underlying data. There's no color data in this particular point cloud, but generally we capture all of the color data. For a given headstone, we're collecting right now with a 36 megapixel camera anywhere between, say, 2 to probably 30 million individual discrete measurements. The accuracy we can predict at tens of microns, so a micron being a thousandth of a millimeter. And if you think of the width of a human hair, that's about 200 microns. I just did an industrial project recently where we achieved accuracies quite easily of 50 microns on machine parts. So here you can see the weathered inscription and the lettering. So even if there's a very small amount of depth preserved on a weathered headstone, we can still make it out. The technique we use to post-process these point clouds is what's called surface depth mapping. The headstone and its inscription is going up and down on the surface. What we do is we apply a flowing mean surface, and then we measure up and down the actual surface of the stone and color code it or assign a grayscale value. This is very flexible. If the stone were continuously curving, then we'd have a continuously curving flowing mean and measure from there. The photogrammetry software generally is commercial. We began with the AtomTech CalibCam software, part of the 3DM Analyst suite of software. This is developed for the mining industry. I still use it for engineering projects, but its high cost, about $12,000 or so US for a single license, makes it prohibitive for cemeteries. Although I would compare that to LiDAR units, which retail for about $40,000 to $60,000. The package we're using extensively right now is Agisoft PhotoScan Pro, a Russian software package, and we can get that for $600 per license as an educational institution, and that pricing may be available, I don't know, for nonprofits. There are other I shouldn't say open, but free packages where you upload your photos, like 123D Catch run by Autodesk. I would really advise against using that. If you read the fine print, once you upload your photos, Autodesk owns them, so that may be something you want to avoid. It also doesn't give the high precision of these other techniques. Once we produce the high-resolution point cloud, we can manipulate the data in one of two open source free software packages, Cloud Compare and MeshLab. Now, photogrammetry, you might get a sense, is really the technology that we've settled on for cemetery documentation. In fact, it would be very difficult for me right now to get my undergraduate students to do an RTI in the cemetery. They don't want to spend a day hoisting up strobe lights. So it is fairly quick in the field. Generally, per headstone, it's about 2 to 3 minutes, if even that. The results, as we're about to see, match or exceed those of reflectance transformation imaging. The software, yes, it can be expensive, but when you think of the overall expense and time saved, we think it's roughly equivalent to RTI. It works well, the photogrammetry does, with the geotagging workflow, which I'll mention in just a moment. The software, however, especially for manipulating the point clouds, can be a bit difficult to use. Now, one of the cons here of 3D recording in general is the size of the data and finding a way to store it long term. And I really have to throw up my hands on this, is that we have no good method of long-term data storage. The 3D data itself, these point clouds can be rather large, over 1 gigabyte per headstone. That said, what I recommend to cemeteries now is that they store the underlying photographs, 6 to 8 per headstone, which you would want to take anyways for good documentation. And then the 3D data can be built on an as-need basis. You can always go back to the photos and generate this data. Geotagging is, I think, an interesting technology, especially apropos the last presentation. We use a Salmita GPS. It's relatively high accuracy, about 3 meters accuracy, at least for a non-differentially corrected system. We could check these points using a Trimble survey GPS where we were getting around 2 centimeters of accuracy and under 1 centimeter if we tried. The GPS unit does also have inertial correction with a triple axis compass and an IMU. So we've sometimes observed accuracies of under 3 meters. One of the advantages of this, it's only about $300, it's added to the hot sheet of the camera, and every time you take a shot, it gives you longitude, latitude, altitude, and I think this is also very useful, bearing. So if we have a cemetery with a headstone with multiple faces, it records the direction the camera was facing each time. This is just freely added, so think of this replacing your photo log in the cemetery. Also apropos of the last presentation, it works nicely with Esri ArcGIS. Here we plotted, not a particularly good base map, this is just Google Earth, of the cemetery. We see the individual color-coded photographs taken by Ian, and then he can click on the individual geotagged photos and bring them up in ArcGIS. And all of this without any operator intervention. They're just sucked up into the software. Adobe Lightroom will also do this. It's a package some of you may use, and you can just click on the individual photos and bring them up. A lot of work, I think, still needs to be done in integrating GPS geotagging into archaeological workflows, and I'd be interested in talking with others who have applications using this sort of technology. This was an absolutely crucial for me in the field. If I'm recording rock art in Jordan, within 5 days with a team of, say, 4 or 5 students, we're recording 15,000, 16,000 photos, so we need a way of applying metadata automatically. So let's now look at some results here. The first thing I emphasize is that these technologies are not miracle working technologies. If there's no depth remaining in the inscription, we're not going to get anything. So here's a sandstone monument and some RTI enhancement applied to it. Yes, we can get a few extra characters, but in the areas that are completely lost, we're just not going to get anything. So I have to be, can't overpromise on these technologies, although I should say we're continually surprised. Within the Sir John A. MacDonald enclosure, we looked at one headstone that was heavily stained and highly eroded by the headstone of Margaret Gilchrist. On the left-hand side, we see a photo taken in 1984 of the monument, and we see the monument around 2010, and you can see the legibility is severely degraded. Here is the RTI enhancement in 2010, and you see many of the characters are now more legible. Now this is a dynamic process, so we can go into the software and apply that filter and move the light around after the event, and to focus in on particular characters and try and get a better understanding of the inscription. When you watch epigraphers use this, they're often just moving the light around continuously, waiting for their brain to sort of spark and see the letters they want to see. Now, let's look at the photogrammetry here. This is a couple of years later. The stone has been cleaned a little bit, but you can see that there's been still a lot of erosion on it. And here is a grayscale depth map of the same stone. If we had time to compare this, you could see that we can see all of the same things we see on the RTI and maybe even a few more characters. And this was data captured in about 2 minutes by an undergraduate student. Here's color coding of the same depth information. And we can also take this 3D surface and apply dynamic relighting to it within software like MeshLab. So here we're taking the surface, changing its texture to essentially a beaten metal rather than stone, and moving the light around until we get the light angles we want to reveal the features in the inscription we hope to see. Here's another stone where there's not a problem with weathering, it's simply low contrast. The inscription is nicely inscribed, it's just very difficult to photograph, so here's a case where we've done RTI and we can dynamically relight it to make it out quite nicely. And we have the comparable photogrammetry data of the same stone. I think this one turned out really nicely. Much less time and essentially the same results. Within the Cataraqui Cemetery, we have a number of Chinese burials from the 20s, 30s, and 40s, and for various reasons, these have escaped the recording by the Ontario Genealogical Society. These are particularly endangered. They're low to the ground and rather humble monuments. We've done RTI enhancement of them, as well as photogrammetry, and you can see here what the point cloud looks like of this data that we can move around. This would be about 2 to 3 million discrete measurements. One of the abiding problems we have in the cemetery is biogrowth, like lichens and algae, on the headstones. These are very difficult to deal with RTI. The lichen often disrupts the surface normals, and we simply can't get any good data. So here's a very difficult headstone where we did RTI, we used various raking light positions, and we still couldn't get it. Now, you might say we could go and clean it, and I've had Masters of Art Conservation students work on this a little bit, but it's extremely time-consuming given the numbers of headstones we have. We were pleasantly surprised by what photogrammetry could do in this application. The lichen still often follows the indentations of the stone. So here's a case where we have a headstone, and we did photogrammetry of it, I think with just 3 shots, and we did depth mapping here. Now, you might say this is not very impressive, but in terms of trying to match up this headstone with burial records, we can see at least the name Margaret here, Grace, which may or may not be part of the name, and some other letters. And this in itself may be enough if we narrow down the location in the cemetery and have a range of death records we're looking at and burial records. This may be sufficient to match up the stone. And we have many marble stones like this with extensive biogrowth on them. Here's an interesting stone, multi-material headstone with granite and a marble insert. We have a few of these in the cemetery. As we'll see in a moment, the marble insert is starting to bow out. The forces involved there are astonishing. And the front of the stone is beginning to spall. Here we did RTI of it in 2010 to record the spalling area. So we got some important dates out of that. And just this past year, the strain built up and the stone snapped. And the marble will simply be stacked in front of the headstone. There's no money for any conservation work on it. What could photogrammetry do? Photogrammetry effectively recorded the bowing of the stone. You can see this on the 3D model here. So if this is something we wanted to monitor over time, we could do it to high accuracy. And think of this as also has applications in conservation treatment before and after in terms of liability issues and others. And then on the right, we can see a depth map, applied the filtering here, and we can see that we get more or less the same data as the RTI. Another problem type of stone for us is weathered marble. RTI has not worked well on this for us, especially where we have this veinous patterning after the weathering. So here's a raking light photo, and here is an RTI enhancement. We're moving the light around, and it's still really not giving us the information we want. But you can see here that the depth information is still there. So here is a color-coded depth map of the same stone. It's significantly improved. We can see that the person buried is Emily Shibley, and we can make out other important numbers on her headstone. Now, I'm not looking here for perfection. Often, just part of a name is sufficient for our purposes. Here's the bottom of the same monument. We see less of that veinous patterning. On the top, you see an RTI enhancement, and the bottom, a grayscale depth map. And we can see from this passage from Revelation 13 that we're getting more or less the same data out of the two techniques. Now, I said at the beginning that RTI produces surface normal maps. Here's a color coding of those surface normal vectors. The blue color indicates that the vector is pointing towards you, red and green, that it's away from you. We can actually apply algorithms to the surface normals to reconstruct the three-dimensional surface and to create a depth map, a grayscale depth map from it. And we did this actually as a sort of apples-to-apples comparison between the photogrammetry and the RTI. So we took that and we took the word right, and we did a visualization, 3D visualization of the RTI data here. I was always told that you can't extract 3D data from the RTI, but here you can see with this character right, as we move it around, you can see real depth information, and you can see the precision of this technique. So now we're producing a similar sort of data from surface normals as we do from photogrammetry that produces that XYZ data. We can also apply color coding according to depth and have a look at it that way. If we now move to a photogrammetry 3D surface plot, so comparing apples to apples, we can do the same thing and look at the same word. We can see we get a little bit more precision, less smoothing in this technique. The accuracy here would be probably around 30 or 40 microns given the lens and camera combination. And here we see the color coding. So I think we've proven that the two techniques are essentially equivalent in terms of accuracy and the data they provide. We really believe that the photogrammetry has the edge with Headstones because of the speed of capture in the field. There are lots of people who've helped out in this project providing funding and moral support and volunteer time. We'd like to thank them by way of this slide. Now, I should say one thing before I end here is that I am always looking for collaborators in this sort of work, and headstones where we can really make a difference in terms of bringing out genealogically or historically sufficient, interesting features on a headstone using these technologies. So please contact me if you have anything you'd like looked at. Thank you.